My name is Melissa Folkerts, and I will be discussing polarity, more specifically polar covalent bonds and molecules. So to begin, one way to think of covalent bonds is different resonance hybrids. So the Cl2 bond is actually almost purely covalent because the two structures with the same energy make equal contributions. The two chlorine atoms actually have the same electronegativity, so they make equal contributions to the resonance structure. With HCl, however, there is a difference in electronegativity, and so the lower energy structure is actually where the hydrogen is slightly positive and the chlorine atom is slightly negative. The chlorine atom actually has the greater electronegativity, as seen from the periodic table here. Chlorine would be all the way over here, and hydrogen is on this side, and the trend tends to go more that way. So the chlorine atom has the greater electronegativity, giving it more of a negative charge, and that structure contributes more to the overall resonance. So this brings us to partial charges, and that is when one atom is slightly negative or positive, and as an example, HCl here, it is depicted by this little symbol, where the hydrogen is slightly positive and the chlorine is slightly negative. This also makes a polar covalent bond, which is a bond in which ionic contributions to the resonance structure result in partial charges, as seen here. And when a partial positive charge is next to an equal but opposite negative charge, that creates an electric dipole. And for an example, HCl here, because hydrogen has the partial positive charge and chlorine has the partial negative charge, the dipole moment is actually depicted here because the arrow points towards the slightly positive charge. Now discussing molecules. A polar molecule would be described as a molecule with a non-zero dipole moment. Some examples would be HCl, as we've seen before, and PCl4 with a fluorine. It's important to note some little easy hint when you're trying to figure out what atoms or what molecules are polar or nonpolar. All diatomic molecules with different elements are slightly polar. As you see here with the HCl, hydrogen and chlorine have different electronegativities, so that would kind of just automatically make it polar. For nonpolar molecules here, they are molecules with no electric dipole moments. So this would be an example, O2 here, and PCl5, and we'll see why later. So one of those important little notes to remember is a homonuclear diatomic molecule, so a molecule composed of two atoms of the same element, are nonpolar because the bonds are nonpolar. So the bond between the two oxygens, as seen in the two chlorines, is nonpolar, so that makes that molecule nonpolar. So a little bit on how shape affects polarity here. We have H2O. Now this molecule, little 3D image here, is more of a bent shape. So when you have the two hydrogens here and the oxygen, there's actually a lone pair here that causes the bent shape. And what happens is there's the slightly positive charges on the hydrogens and the slightly negative charge on the oxygen here. So this molecule is actually polar. If you compare that to CO2 here, this is a linear shape. The oxygen in the middle has the octet here, and the carbon atoms right here have the 2 electron pairs that are lone pairs, and what happens is it causes a linear shape, and this causes both of the carbon atoms to have slightly negative charges. So as you see here, the 2 bonds to the oxygen are polar. However, because of the shape, they cancel each other out, making this molecule nonpolar. For a more complicated molecule, we have a trigonal bipyramidal shape here. And if this were to be PCl5, all the bonds would be polar. However, because of the shape, it's a little bit more evenly distributed. This shape here would cause the dipole moments to cancel each other out. However, if you had something like PCl4 with a fluorine, say one of these here is a fluorine, this one up top here, they would actually not cancel each other out because fluorine does have a different electronegativity. It's a bit stronger than the chlorine atoms.